Alright, let's start getting some of this key underway. I don't think we'll get it done all at once, but create a monolinear Lusona. A Lusona with 2 curves and a Lusona with 3 curves with respect to the plated algorithm. So this requires that understanding that the greatest common divisor of the grid dimensions tells you how many curves you're going to have. So if I want something that's monolinear, I need my array of dots to be something by something where those two numbers something like so P rows and Q columns, so that the biggest number going into P and Q is 1. So 2 by 3 works, for example. If I take a 2 by 3, that's monolinear because the largest number going into 2 and 3 is 1. If I want 2 curves, I can do something as simple as a 2 by 2. The largest number going into 2 and 2 is 2. So there's one, there's another. That would be the same for 2 by 4. The largest number going into both 2 and 4 is 2. So you'd have something like this. There's one component or one curve. There's the other one. If I want 3 curves, I need the greatest common divisor to be 3. 3 by 3 is the easiest one, or the smallest one. So, and this is the one that ends up being the tortoise. You can also do a 3 by 6. That would work as well. Oops. Let's see. Oh, I goofed. Let me try that again. The 6. Alright. So there's 1. Be careful here. There's 2. And there's 3. A couple examples. So there are multiple answers to number 1. In number 2, the idea wasn't that you'd have to draw them, but you can. But you're using this fact. So the greatest common divisor of 2 and 2 is 2. So it's multilinear. These numbers, the greatest common divisor is 1. It's monolinear. That's monolinear. That's multilinear. Monolinear. 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 Because these are the largest numbers that go into both of these numbers, which are the dimensions of the grid of dots. Now, as for break lines, the whole idea of break lines is that you can start with something that has more components and reduce it to less components. So let's I'm going to grab some colored markers here. So the prototypical example that I usually go to is the 3 by 3. So here's a 3 by 3. And of course you can watch the video on break lines. But the idea being, if you draw a break line through 2 different components, 2 different curves, that you're going to stitch those together. That is, if I redraw this, if I do, here's my orange curve, I can't finish it though. I end up having to traverse the green curve. So I was able to reduce the curves from 3 to 2. Now I can reduce those 1 further by cutting across these 2 components. So if I put a break line there and a break line there, and these break lines, they essentially prevent me from finishing. I can't finish. So I just have to keep rumbling around until I get back to the beginning. So there's a monolinear. So that's one example. There are others. And then what happens when you take 2 monolinear sona and overlap and join them at one point? We saw this in the group work. The idea is, let's just do a quick run through. But if I took a 2 by 3 and another 2 by 3, these are themselves monolinear, right? And overlapping at one point, here's the understanding. Imagine that you were to snip the curve here and then kind of open up this side and this side and stretch them over here. And then you were to snip this piece and open those things up. And then if you were to join those, well, if you're going around this monolinear Lusona, and then you take a break and you go over here, you can trace out this entire thing, returning right back to where you entered the Lusona, and then return right back to where you left off in this Lusona. This doesn't work if they're multilinear, because there are different components. Essentially, this is an extension of the idea that if I have a, say, a 2 by 3, that I can, that before I finish this, I can do all kinds of funny things before I come back. It doesn't change the monolinearity. If all this funny business ends up being another monolinear Lusona, then that's fine. Now imagine you shrink this bridge so that these 2 points overlap. So then you'd have something like this, except now the 2 grids are sharing one. And it's still monolinear. Try some examples with multilinear to convince yourself, but that's the basic idea. So what are we at? We've checked off that one. What happens if you take a monolinear Lusona and add a square grid onto one of the sides, creating a new Lusona? Well, there's a video on that. And the idea is that squares don't affect mono or multilinearity. As a way of understanding that, suppose I have a 2 by 3, and I want to add on a 2 by 2 to it. So what would happen? Well, as I was going along this line, I'm now not going to bounce off this wall. There's no wall. So the line continues, bounces around the square, and because the square is not monolinear, and the square is symmetric, where you enter this grid, you exit. And then you travel around your Lusona, you get here, and you're not ricocheted out of the corner. You continue into the square again, heading, and you exit right where you entered. So this keeps you from adding any components. And this would work with a 3 by 3 or a 4 by 4 or a 600 by 600. Provided you had a big enough sonnet to attach it to. The square cannot be any bigger than the longest side of the Lusona that you're attaching it. So if you have a monolinear Lusona and you add a square grid to it, it's still monolinear. And this is an idea we've been using in the Celtic knot stuff. If you have a monolinear grid of boxes, something that will create a knot as opposed to a link, and you add another square grid to it, it remains a knot as opposed to a link. If you start out with something that's multilinear, say a 2 by 4, and you add on a box to it, it will remain multilinear. So if and really all that square has done is to add a little lobe. So add a little lobe to that component. There's still going to be 2 components. Here's the other one. Remember the 2 by 4, if I cover that box, has these 2 kind of V components. And when I'm adding on the box, it just extends each of those components. It's still 2 components. So adding squares doesn't change the linearity. Break lines, again, they're generally pretty visible. It's a couple of ways you could answer this question. You could use sentences, arguments, pictures. So right now it's a 5 by 6. Would it fit on a slightly smaller grid? That is, what would happen if you deleted the bottom row? Well, if you deleted the bottom row, you can kind of see what would happen, what those break lines would do. You'd have this broken border on the bottom. You can do a quick experiment with regards to this. Just by making another grid, we can make it say just 2 to see what that would do. What if you had something like this, something like this, something like this? Well, now, as you try to work your way around here, you're not quite getting this form. Right? This is what you'd see at the bottom. You see those two things, right? So you'd get these breaks along the bottom border. But the Flight of the Wild Hen has this consistent border. This they're all enclosed. There aren't these breaks. So that's one way you could argue it, just by example. Look what happens. Another way is you can say, well, if you look at the fundamental chunks of these designs, I need 3 rows to fit a line of dots above the break lines and a line of dots below. And then I need some sort of minimum number of columns. And you can do some experiments there. Would it work to have, say, this many? And the answer is no. A 3 by 3 won't quite work. There's not enough room for this break line. Notice how there are some dots there. And you can test this. Again, part of the neat idea of these things is you can test your ideas out. You can do an experiment. So if you did something like this, and then tried working out, and we're not asking about monolinearity right now. So there's something reminiscent of the Flight of the Wild Hen. You've got this bit, but you've got a break in the side, which you don't have here. So this might be an argument against it. Compare, for example, an experiment on a 3 by 4. And this is something we haven't done enough of in this class, is experiments. You can really construct this knowledge on your own. So let's see. All right. So there we have a continuous border. All the dots are enclosed. There are no breaks, and we have this S shape. So a 3 by 4 will work. And this is sort of the smallest chunk you can have. All right. So if you think of it, if you want to add on more, you can. You can go from a 3 by 4. You can add on 2 more rows of dots, extending this break line and making room for the next set. So every time you go over, it would be +2. And if you want to go down, you need to keep this row, and then you need to add 2 more rows, so it's +2 down as well. So you have to jump by 2s in either direction, starting from say a 3 by 4. So that's you can several ways you could argue this, by example or more general. But that takes care of the first page, so I think I'll stop there.